Hello everyone. In this video, we are looking at another important data type in Python, that is floats. These are numbers with decimal points, and in bioinformatics, you will find them everywhere, from expression values to quality scores. What is a float? A float, short for floating point number, is simply a number that has a decimal point. Floats are very common in bioinformatics when we are working with expression values, statistical results, or anything that needs precision beyond whole numbers. Let's open a Jupyter notebook and see how floats actually work with some practical bioinformatics examples. Let's start by adding a markdown heading to title this section. Defining floats in Python. This helps keep our notebook organized. I am adding a comment to explain what this variable represents. This is a transcript's expression value measured in TPM. Expression underscore TPM equals to 23.89. Here I am creating a variable called expression underscore TPM and assigning it the float value 23.89. The decimal point makes it a float. Print expression underscore TPM. Now I am printing the value stored in expression underscore TPM. This will display the number 23.89 in the output. You can see Python shows us 23.89 just like we assigned it. It keeps the decimal, confirming it is a float. Print type expression underscore TPM. Now I am printing the type of this variable using the type function just to confirm that Python sees it as a float. And the output says class float, which confirms that Python recognizes this as a floating point number. Let's add another comment. This time we'll store an average sequencing quality score. Average underscore quality equals to 37.5. Here I'm creating a variable called average underscore quality and assigning it the float 37.5. Print average underscore quality. This should display 37.5. And just like before, the output is 37.5, so everything looks good. Print type average underscore quality. Again, I'm using type function to confirm that Python treats average underscore quality as a float. And we see class float confirming that average underscore quality is stored as a float. Now I'll add a comment for the next variable. This is an e value commonly seen in BLAST results. E underscore value equals to 1.2 e minus 50. I am creating a variable called e underscore value and assigning it a float in scientific notation 1.2 e minus 50, which means 1.2 times 10 to the power of minus 50. Print e underscore value. The output shows 1.2 e minus 50. Python keeps the scientific notation because it's a very tiny float. And finally, let's print the type of this variable to verify it's a float. And yes, Python tells us class float, so even scientific notation is treated as a float. Float operations. Floats can be used in calculations just like integers. You can add, subtract, multiply, or divide them. You can also round them or compare them to other numbers. These are especially useful when setting thresholds like quality score, cutoffs, or significance levels. Now let's try some float operations commonly seen in bioinformatics workflows. I am adding another markdown cell here to label this next section float operations in bioinformatics. We'll start with calculating the average expression across 3 transcripts. I'll add a comment to explain what we are doing. expression 1 equals to 21.4. Here I am creating a variable expression 1 and assigning it the float 21.4 representing expression for the first gene. Expression 2 equals to 25.7. Now I am doing the same for the second transcript. Expression 2 is assigned the value 25.7. Expression 3 equals to 24.5, and here's the third transcript with the value of 24.5 stored in expression 3. Average underscore expression equals to expression 1 plus expression 2 plus expression 3 divided by 3. Next, I'm calculating the average by adding all three values and dividing by 3. The result is stored in average underscore expression. Print average underscore expression. The result is something like 23.86666666 and so on. Python gives us the full precision float. Now we will round that average to make it easier to read. I am adding a comment to describe that. Rounded equals to round, and within brackets I'll write average underscore expression comma 2. Here I am using the round function to round the average to two decimal places. The rounded value is saved in a variable called rounded. Print the rounded average. Now we get a cleaner result, that is 23.87, which is much easier to read and compare. Now let's move on to comparisons. I'll add a comment here explaining we are checking quality. Print average underscore quality is greater than 30. I'm checking whether average underscore quality is greater than 30. This will return either true or false, and the result is true, meaning that the quality score passes our threshold. Next, we'll check if the E value is below a significance threshold. I'll note that in a comment. Print E underscore value is less than 1 E minus 5. We are checking whether E value is less than 1 E minus 5, that is 1 into 10 to the power minus 5. That's a typical cutoff for blast hits. The output is true, which means this E value is statistically significant. Why floats matter? So why do we need floats? Because biology is full of precise, continuous measurements. From expression levels to probability values, floats let us capture the details we need to make informed decisions from our data. To sum it up, floats help us handle numbers that aren't whole. You'll use them constantly when working with quality scores, expression values, or statistical cutoffs. Thank you for watching. If you found this helpful, don't forget to like, share, and subscribe for more beginner-friendly bioinformatics tutorials using Python.